So we will finish this proof. We basically have this language L which is in d time Gn, and we want to show that it is not in d time Fn. So suppose it is, and it is decided by this Turing machine M in time c dot Fn for large n bigger than n0. So what we will do is we will look at the descriptor. Now Turing machine M has actually trivially has infinitely many descriptors. So let's pick a large enough descriptor y and see what we can do with that. By large I mean that g of y should be bigger than f of y times log of f of y. Okay, for all y greater than equal to n0. So this is by large I mean that g value should be bigger than f times log value. What is this? Why do we need this? So see, the idea is that we want to simulate my on y. Okay, and this simulation will be done by a universal Turing machine, which will take this much time, d times f times log. So this can be done in d times fy log of fy for some d. Universal Turing machine can do the simulation. This we had seen when we did Cook-Levin reduction. You saw the details, right? That configuration is changing, and you basically have to keep track of the configuration, and that way you can simulate any given Turing machine. But the trivial idea takes quadratic many steps. Okay, time complexity becomes t square. Here we are claiming t times log of t. That is the best result known, and this I leave as an exercise. Okay, so UTM can do this simulation. Or let me say fast simulation. Okay, so a universal Turing machine can do this fast simulation. It's fast because it is almost linear in the original time complexity, which was c times f of y. Okay, so when you simulate, then there will be some blow up because you have to keep overhead. You have to remember the tape information on the tape of universal Turing machine. So all that checks and balances blow up the time, but it don't blow up more than a factor of log. Okay, so this you will do I think in one of the assignments. So once you have done this, then now we can go ahead with the simulation of y on y. Okay, Turing machine y on input y, and ask the question, what is d of y? Right. So D is solving L and M is solving it faster. That's what we have assumed. And M's descriptor is now given to D. So what will happen? Okay, there should be a conflict. There should be a conflict because of step 2.2. Step 2.2 is the reason why the contradiction will happen. So let's go through that contradiction. So note that my of y is my runs y is a descriptor of m, right? So m sub y is the same as m. So it runs for time c times f of y and then halts. Right, m always halts. It's actually deciding L in this much time. It always halts in this much time. So which means that D halts on y in time because what will D do? D will be simulating my on y, right? So D simulates this in step 2, sorry. So D will be simulating my on y, which originally on itself it would have been possible in c times fy. It halts in its time complexity is c times fy. On simulation it will blow up to how much? So when D simulates this, it will blow up to D times f of y times log f of y, and which we have assumed smaller than g of y. So hence it will be possible in step 2 because the simulation time is actually smaller than the time D has in step 2, right? So it will actually give an answer and it will follow 2.2. So which means that step 2.2 gives output 1 minus my, right? So this means that dy is not my. Right, but haven't you assumed that M and D both are solving the same problem, which is L, right? So this is a contradiction. So this contradicts M solving L. Okay, and this means that M doesn't exist. Right, that is what we had assumed, that there is a faster Turing machine for L in time CFN. So that cannot happen. So M can't exist. And once you have shown that, you have an extra problem in d time Gn. So d time Fn is not in is a proper subset of d time Gn. Okay, so we actually are able to construct a problem which is a bit artificial, but our motivation or inspiration is clear. It's from the halting problem proof, the diagonalization argument, and this is something which cannot be solved faster, at least not as fast as order Fn. So similar thing we can do with space complexity class. Then we call it space hierarchy. So space complexity class is as the name already suggests, these are problems which are solvable in order Fn space. Right. So P space, for example, is polynomial space. So you are looking at problems that are solvable in n to the c space for constant c. And here again we can have a similar argument as before. So that's our theorem 2. So if Gn is more space than Fn, then space Fn is strictly smaller than the class space Gn. So here again we have to design a problem which is extra in space Gn. You can already notice the parameters being better than what you had in theorem 1. So in theorem 1 you needed G to be more than Fn times log Fn. Right? This is little omega. So remember, little omega means that Gn divided by Fn log Fn should tend to 0. But now we are asking only Gn by Fn to tend to 0. Okay, the log factor is gone. So this is actually an optimal condition. So space hierarchy theorem is better than time hierarchy, at least what the results are known. This happens because of the simulation. You can simulate in the same space, while time was you take more time. Okay, at least the proof we did. So the idea is like before. So again, define a Turing machine D as before. And the advantage here is because of the simulation, as I said. So note that universal Turing machine can simulate y on y. Okay, the Turing machine y descriptor on itself in roughly the same space. In roughly the same space as that of Turing machine Y. Okay, so that's the proof sketch. So what will happen is you can go back and see the proof. So it's the same D. Okay, that basically you will simulate it for that many. Instead of steps, it will now be space. And if it doesn't halt, so I'm reading step 2. So step 2 will be now, instead of step, it will be space. And that will define D. And in the proof, when the simulation happens in step 2, there you can simulate in within GN. Okay, you will not need this or you can simulate within Fn. So let me maybe write down the at least the descriptor. So D is same as before. On input X, if X is not Turing machine, output 0. Step 2, else simulate the descriptor X Turing machine on itself in G of X space. Okay, that's the only change. If it doesn't halt, then you don't have any answer, you just output 0. Else output the opposite. Okay, so simulation, since simulation is faster now, I mean, not I shouldn't say faster, the simulation can be done in almost the same space. You can finish the proof. So I leave that as an exercise. Finish the proof by contradiction. Okay, so that would tell you that space Fn is strictly smaller than space Gn. And what is an open question here? What's open here is so make theorem 1 as strong as theorem 2. Okay, is that possible? So in theorem 1 you had this G more than F times log F. Can you prove the same thing for G more than F? So which is the same as asking that D time Fn is it different from d time Fn times log Fn? So this we don't know. Okay, whether if I give you a logarithmic factor more time, can you solve more problems? Now obviously this should be true, but we don't have a proof. Right, for space we know. For space this is, we have just shown it. So for space we can show this, but for d time we don't know. Okay. Now the final thing is, after time space we will look at non-deterministic or non-determinism as a resource. So non-deterministic time hierarchy theorem. So these will be theorems by Cook, and Zach. Okay, we will present their proofs. Now this will not be very easy like it was for time and space hierarchy theorem. This will be more complicated. So the proof here is quite involved. Why can't you just do what you did in time hierarchy theorem's proof? So the problem here is that this is defined in terms of accepting path. So, and in the extra problem that we designed, we used because of diagonalization we negated it. So when you negate it, you go into the co-class. Okay, and co-class creates a problem. So the issue is negation. That takes you to co-class. Okay, so for an NDTM M, we don't know if the computation one minus mx can be done by a fast NDTM. So fast meaning up to log factors, up to polynomial blow up, whatever, because the trivially if you just negate, then there is an exponential blow up, right, because of the number of non-deterministic bits. So trivial is exponential blow up. Right, so this type of a non-deterministic time hierarchy will be from Fn, it will directly jump to 2 raised to Fn. Okay, so those classes you can show by the same method as before, that they are different. But then when G is closer to F, closer than exponential, then this method will not work because of the way we have defined NDTM by making 2 choices in every step. So anyways, we have to give a more elaborate proof here, and fortunately we will be able to show that if Gn is more than Fn, then n time Fn is strictly smaller than n time Gn. Okay, which is as you can see, it's optimal, right? Both theorems 2 and 3 are optimal. Ironically, for time d time we don't have such a good result, but for n time we will show this, right? So that's how do you do this? That's a mystery at this point. How do you do something better for n time than d time? So the idea is to design a Turing machine on the RHS that differs with any Turing machine you take on the left hand side. In very rarely it will differ. In very few inputs it will differ. Okay. But that is enough to show that the Turing machine you have created is extra. It cannot be on the left hand side. So design this again, this extra Turing machine D in RHS that differs with the LHS but very rarely, on very rare inputs. Okay, so in fact it will be not wrong to say that I mean, if you are looking at thinking of n bit input, then D will differ with a particular Turing machine on the left hand side on very small sized inputs. Or I should say that, okay, the difference actually jumps exponentially in n. Okay, the strings up to length n on which D and some Turing machine on the LHS will differ, for n they will only be log n many. Okay, you can think like that. So it will be very rare difference in the answer. So on average case, actually D will be solving the same problem as on the left hand side. So actually negation requires few non-deterministic bits. Okay, so this is how we will tackle negation. We will make negation require very few non-deterministic bits. So this is in fact called lazy diagonalization. Okay, it will be lazy diagonalization because it will happen after exponential steps. Like it will happen at 2, then 4, then 8, then 16, then 32, and so on. In fact, this will be even worse. It will be lazier than exponential. So, for this purpose, we need a very rapidly growing function S such that g of, so we are defining S, right? So, g of S of I plus 1 and 2 raised to g of S of I, and then you add 1. Okay, these two should sandwich S of I plus 1. Fine. So, in particular, this is, say, we are saying that S of I plus 1 should be growing, if you look at SI, S of I plus 1 is exponentially larger, and there is also g involved. So, it is more than just 2 raised to SI, and g, and the other condition is kind of trivial, g of SI plus 1 greater than S of I plus 1 for all I. Okay, so this is a very rapidly growing function. We will use it next time.